Okay, so today we're going to learn our last basic rule, which is called the chain rule. Okay, so suppose I gave you a function like this to differentiate. We know that we would just simply write that as 3x plus 1 times 3x plus 1, and we would use the product rule, okay? But what if we had something that was to the 20? Obviously, we're not going to expand that, so we need a rule for something that looks like that, okay? And this takes us back to advanced functions and our knowledge of composition of functions. You'll remember that this is the composition of g and h, okay? So, for example, we would see something like this, like let's suppose that g of x was x to the 20, okay, and let's say that h of x was 3x plus 1. Then we know that g of h of x would equal g evaluated at h of x, which is 3x plus 1. And when we take 3x plus 1 and we sub it in for x into g, we get the composition of the functions. Okay, so that's how we create this scenario where we would use the chain rule. Okay, so in calculus, we're not so interested in creating these functions, but identifying them. Okay, so I just want you to take a look at these functions for a minute, these four, maybe pause the video and decide which ones you think are actually composite functions, or is it just simply a sum and difference, or a product or quotient function. Okay, so really quickly, hopefully you can see that this is simply a quotient of functions. Okay, if we take a look at B over here, this one is an example of a composition of functions. Okay, so if we say f of x is this, which of course, remember, just means a bracket to the exponent 3 over the imaginary 2 that's over there, we could say that the inner function, okay, the h of x is the 7x squared plus 2x plus 8, and the outer function, the g of x, would be x to the 3 over 2, right? Okay, and we would do their composition, and we would get back to that f of x over here. Okay, taking a look at C, hopefully you can see that this is also a composition of functions, much like the one above. So our inner function, our h of x, is x squared plus 7, and our outer function, our g of x, is x to the 7, right? And you can remind yourself of composition of functions. And of course, this one right over here, this one is simply a product of two functions, okay? So we're going to learn now how to take the derivative of these composite functions. Okay, so to take the derivative of these, we use what is called the chain rule. Okay, so here's our function that is a composite function, and to do this then, we first start on the outside, so we take the derivative of the outer, which is like the g function, so we have g prime of h of x, and then we go inside, and we take the derivative of the inside, the h of x, which is of course h prime of x. Okay, so just using some of the other notations, we've talked before about this Leibniz notation. Okay, so that simply says that if y equals f at u, okay, and u equals g of x, okay, then the derivative of y with respect to x is first we take the derivative of y with respect to u. Okay, so that's like our outer function. And then we're going to go inside and we're going to take the derivative of u with respect to x. Okay, now here's where I start to have my own little way and my own personal little way of writing this. Okay, and I would say here that if y, our function, was some blob, I call it a triangle, to some power, okay, then the derivative, y prime, is simply, we start outside, so the outside, we're going to bring down our n, use our power rule, triangle to the n minus 1, and then we multiply by the derivative of the inside, which is triangle prime. Okay, so we'll get to what that means in just a little bit as we go through some of these examples. Okay, so let's take our very first example. Okay, so for me here, you can see in this first example, this is one of the ones we were doing originally. This is my triangle. Okay, and so I'm going to start simply by working on the outside here. So I have triangle to the 7, so the derivative would be, of course, 7. Triangle to the 6. That's just using my basic power rule. And now I'm going to go inside and take the derivative of the inside there, and everything gets multiplied, and that would, of course, be 2x on the inside. So that one starts out pretty simple. We do a little bit of simplifying. Okay, we always want to take the monomials and leave them in the front, and other than that, we obviously don't need to expand this 6 times, but we do want to simplify and make it look proper in factored form. Okay, so by doing that, we would of course get 14x, and then x squared plus 7 to the exponent of 6. Okay, let's try another one. Okay, so let's take a look at b here. We have the square root of 6x squared minus 5. So first we want to make it look like a composite function, and sometimes it's hard to see like that, so of course hopefully you remember that this is the same as 6x squared minus 5 to the exponent of a half, right? Okay, and this is still f of x. Okay, so now again, I'm looking at this as some blob, some triangle to the exponent of a half. So let's take that derivative now. We have f prime of x. Okay, we're going to take the derivative of the triangle to the half, which is going to be half the triangle. Subtract 1, which we get negative 1/2. Okay, now I'm going to go on the inside and take the derivative of the inside, which is, of course, just 12x. Okay, and these ones are a little bit more challenging. We want to simplify them. So hopefully you can see that this 12 divided by the 2 leaves us with 6x, and that's actually all we have on the top, because now this piece right over here ends up moving to the bottom and becoming positive a half, which is, of course, just the square root of 6x squared minus 5. So hopefully that simplifying makes sense to you. That's the little bit of practice that we are going to have to do here. Okay, similarly, let's take a look at question C. Okay, and some of you might look at this question C right here and be tempted to use the quotient rule, okay, for this one right here, because you do see a quotient. But I'm going to and it would work, it just gets challenging because when you take the derivative of the top, you end up with actually 0. And I always encourage people not to do that. The simplifying is much more complicated. If you just rewrite this, so this function can, of course, be written as negative 3 the whole denominator 2x squared minus 3x plus 1 to the negative 3. Now you can see that it's a very simple chain rule, and the simplifying becomes a lot easier. Here's my triangle. Okay, so I have negative 3 triangle to the negative 3, and now we're going to take the derivative of that. Okay, so let's take this derivative here. We're going to start with just our power rule for our triangle, so when I bring that 3 down, I get, of course, positive 9 times the triangle, sorry, that's a 2x squared right there, minus 3x plus 1 to the negative 4 when I subtract 1. Now I'm going to go inside and take the derivative of that piece right there, and the derivative is 4x minus 3. Okay, so now in terms of simplifying again, let me just remind you that we have this 9 on the top, we have the 4x minus 3 on the top, and we can take this whole thing to the bottom and it can become a positive exponent. So when I do that simplifying, okay, you can just leave it in factored form. There is no need to expand the 9 times 4x minus 3, although if you did, that would be totally fine, but it's not necessary. And then on the bottom, I have 2x squared minus 3x plus 1 to the 4. Okay, so hopefully these make sense to you. Hopefully you can follow, and we're going to practice lots of them tomorrow in class to make sure that it all makes sense. See you tomorrow.